get started. Just going to make you guys smaller here, but if anyone has any questions along the way, just feel free to speak up. This is taking up my entire screen here. So the goal of this for me is to kind of give a little bit of background education on what the technique can do, how to use it, and then tell a story, right, on two of these case studies that I performed over the past couple years. So some background on TA, we make a lot of different kinds of instrumentation. You can categorize these broadly into thermal analysis and mechanical testing. Today, I'll be talking about a thermal technique. So you can see my mouse, this guy right here in microcalorimetry, the TAM4. So for isothermal calorimetry, in principle, it's very simple. Right, we're just measuring heat flow or the rate of heat generation versus time. Right, that's our raw signal from this big calorimeter on the left. That's a floor standing unit. So with the heat, right, we have something happening, right? The nice thing about calorimetry is that it's a universal detector. Chemical reactions, physical changes, phase changes, electrochemical reactions. If anything is happening within the system, it will produce some sort of exothermic or endothermic heat flow response. Just an example to show off the sensitivity here. So this is obviously not a battery, but in this case, we have a millipede, right, in an ampule. And what we're measuring here is the metabolism, so the heat generated from it digesting a single blade of grass. And we can see that's about 100 microwatts, right? Those little spikes in the signal are from the millipede physically moving around. You could see a negative slope as well as it starts to slow down due to the consumption of oxygen. This is a sealed vial. And I'll have to make a disclaimer, no insects were harmed in the course of this experiment. It was removed before it ran out of air. And a different experiment, but we don't show the data, but we did a similar experiment where we put a single ant inside the same ampule, and it was giving around 30 microwatts of signal. Now the TAM is sensitive down to, I think, plus or minus 100 nanowatts for the coin cell calorimeter. So it's kind of sensitivity dependent, depending on which calorimeter you're discussing, but the coin is the one that we'll be discussing partly today. So nanowatt levels of sensitivity. So you can see that this is a pretty large signal relative to what we can measure. So an extreme level of sensitivity that we apply to electrochemical systems, right? In this case, a battery. Right, so we can see in red our voltage, and then in blue, this is an example of a typical heat flow response during charge cycling. Right, we see a lot of features here from both structural changes in the active materials, the energy storage reactions, and side reactions, right? We're seeing everything here. Now, for those of you a little less familiar with operando testing, this is getting more in demand nowadays, just so you can measure multiple things at once. Right, you have a traditional ex situ characterization of the materials level, where you're getting a lot of that structural chemical information on the materials. And you can couple that with the real-time use of the device, right? So this allows you to directly correlate in the time domain, right, these material level changes with changes in the electrochemical behavior, right? So it's a very information dense technique. Some of the special advantages to calorimetry in particular is that it's sensitive to everything, right? Any chemical, physical, or electrochemical change happening inside the cell, you're having all three of those occur over time, is something you can detect. So it's been traditionally used in new material research, a lot of publications in academics lab, fundamental research, formulation, screening, and optimization, things like that. But because of this second point, that you don't need any special cell requirements, that also means it's compatible with commercial format cells, right? It's not a special cell configuration to do this test. You can just go to the hardware store, buy a battery, and put it in the calorimeter. right? So this opens up the door to doing things outside of R&D, like lot testing and QA/QC, even some forensic analysis or cell qualification for people that are just purchasing cells. So in that vein, I wanted to present 2 case studies where we did just that. We purchased some cells and we did some testing. So I'm just going to jump right into that. So just some background on this. The goal of this testing was not to produce interesting data. It was just for product training. So we launched this kind of package in late 2023. I was training a new employee, or rather an existing employee, in this new technique. So I told them, go to the hardware store, buy some rechargeable coin cells, and we'll test them. So we did just that. He got a twin pack shown here. You can see from the labeling that they were both newly made in 2023, and they both passed QA/QC. Right, so we weren't expecting to get any kind of interesting results, but we did, unfortunately for the cell manufacturer, or fortunately for this presentation. Before I go into the actual data, I want to discuss what normal behavior looks like first, just to put this into context. So you can see this data on the right. We have our voltage in blue and our heat flow in red. I'm going to point out a couple things. First is that this thermogram profile in red, if you look at it from cycle to cycle, is highly repeatable. Right, we see the same major features with the same magnitude, right, when the cell is stable. Right, our baseline is not shifting, it's flat. Right, so we have roughly the same level of heat generation per cycle. Right, and this thermogram, the exact peaks, the shape, the magnitude, that's characteristic of the cell chemistry. The heat flow is very sensitive to changes in formulation for that exact reason. So if you're suppressing certain reactions, or if there's slightly different changes in the active materials, that's going to show in the heat flow.
Is positive heat flow exothermic?
Yes.
Thank you.
So that's a convention thing. You can actually switch it in the software, I believe, but in this case, positive is exothermic. So next slide, I'm going to show the data. So coin cell number 1. So I'm making these anonymous just to not make any manufacturers angry. So coin cell number 1, the first cycle looked fine, right? Nothing wrong with it that I could see. But as we continued to cycle, I'm just going to show the heat flow from now on. Right? So if you notice, there's a slight increasing trend in the magnitude. Right? So I'm going to draw a straight line across at 0. Okay? You can notice that per cycle, there's a slight increase in the heat generation. Okay, so this jumped out at me as something that's not good, so I dove a little deeper. I'm going to overlay these so we can kind of look at the trend. So you can see, right, we have this shifting upwards and then to the left. Now the left shift is just due to a reduction in capacity per cycle, right, because this is plotted versus time. Now the general increase in heat flow, because when we look at this, it's not, I guess I'll plot the data here first where you can kind of see it, right? Just the increase in total heat and the reduction in capacity. But looking at the thermogram itself, there's not a particular peak that's increasing and everything else is staying the same. It's almost like a general shift upwards throughout the entire thermogram. Right, what this is telling me is that there's a change in the joule heating, so a change in the internal resistance. So it's shifting this entire heat generation profile upwards. Right? And it's doing so at an alarmingly high rate. So this is definitely abnormal. So something is happening just to cause this accelerated aging in this cell. Normally, this is a characteristic of a cycle age cell where you have an increase in internal resistance this high in order to show or cause a shift in the total heat flow thermogram. Here it's happening very fast. So this is bad. if we're from a quality control standpoint. But it was the only thing that I could tell that was wrong with the cell. Now the second cell, I'm going to show the data for that. Also not good, but something entirely different was happening. So you can see in red, the first cycle, we have this massive exotherm during cycling. And the second cycle, it's still there, but it's much lower in magnitude, right? It kind of goes away after the first 5 cycles and returns to normal, right? So something is happening to pacify the reaction. Some sort of enormous background reaction is happening. I'm going to show some overlays just to highlight this a little more. So cycle 2 through 5, I'm overlaying here. You can kind of see the passivation here. Interestingly, right, when you look at just the voltage data, there's nothing abnormal happening. All right, so it's some sort of background reaction that's not directly affecting even the capacity, right?
What is the nominal watt hour so that we can have an idea of what those watts mean with respect to the watt hour nominal energy capacity of the cell? Thank you.
So this was a 40 milliamp hour cell, so it's a coin cell. So pretty small, right? But relative to this normal behavior here, you can see the intensity of the thermogram is much higher. It's like actually probably closer to 5 times higher, right? And
Thank
that
you.
first one is much higher than that. So the interesting thing about this is when you zoom in a little, this is just on cycle 5, you could see that the reaction both initiates and continues into the open circuit rest period. So this is about 1 hour, right? On the right, that's cycle 6. This is typically what you'd see. This is normal behavior where you can see the heat flow is about 250 microwatts. And then during the rest, we have a thermal relaxation up until the beginning of the discharge. Now, when there's some background chemistry happening, like in the electrolyte or like a chemical reaction between the interface and the electrolyte, then you start getting more activity like you do here. Right? So there's definitely something happening.
Sorry, Jeremy, could you remind us what the chemistry of this was?
They didn't say.
Oh, okay.
So that's the fun part about testing commercial cells. They don't always say. From the thermogram, I can tell that it's a graphite anode. I would guess because of the voltage range, it's either NMC or LCO, and kind of some of the other features in there. No idea on anything else as far as the additives or electrolyte blend. So yeah, we have this reaction occurring during the open circuit period as well. After cycle 5, we get kind of a stabilization, right? We see more normal behavior, right? A slight shifting due to loss of capacity over time. Voltage curve continues to look normal. And then our heat flow, right, is stable, right? This is contrary to cell 1 where we're seeing that shifting upwards. So I just also wanted to show this just to show what normal behavior looked like. So in summary, I'm just overlaying all of these together, right? We have this kind of distortion in the voltage curve on cycle 1, right, from this very large reaction that's occurring. Interestingly, the capacity actually went up after this first one, so something to do with freeing up lithium in the system. I think maybe the breaking of some sort of like encapsulated lithium deposit, if I had to guess, and then the subsequent reaction with the electrolyte. And then we see a gradual passivation through cycle 5, and then it stabilizes. So in conclusion with these, I think really the only thing I can say is that they should not have passed QA/QC. Right, we had 2 distinct degradation modes that were much higher than should have been seen in like a stable commercial cell. And I'm assuming they were made in the same lot since they were packaged as a twin pack, right? So something definitely went wrong with that lot. That using a more advanced technique like this would have caught some of those errors, like in the manufacturing process.
So Jeremy, just to ask about that, after a couple of cycles, you show that it actually calms down.
It does. Yeah.
So is it out of spec once it's calmed down?
Well, they didn't give a lot of specifications in this case, but
So let-
from what I looked at, it looked pretty normal actually after it calmed down, better
Okay,
than the first cell.
correct. So it has calmed down into a certain chemical, electrochemical signature. And if that's within spec, does it really matter? Statistically, yes, we can show that there was a big something happened at the beginning, but
Yeah,
if they released that cell after 2 cycles as part of the manufacturing process, so that you would never see that in the field, say,
yeah.
then the end customer might never see it. In fact, the end customer may never see it either, not realizing that the first use case was a little bit flaky, say. But does that actually affect the performance of the customer? I don't know. And you might want perfection all through time, but on the other hand, we always what happens in the cell at the very beginning is always different than what it's doing in when it's actually used over time.
Oh, that's true. That's a good
Bad way of
point.
saying it,
So,
but
in the case of the first cell, I mean, we are seeing an increased rate of degradation and increased cell heating. That will decrease the lifetime of the cell. So, whatever uh,
so
specifications they gave for lifetime is definitely not going to meet that. The second cell, my concern is that I don't know what caused those very intense exotherms,
yeah.
right? If that had happened during like the wrong type of use case, like a rapid charge or discharge or at high temperature, that could have caused some, a potential damage to some of the other components or swelling or something like that. I don't know if it'll
Mhm.
happen again later, right? This for me is like a stability thing, a safety thing,
Okay.
right?
Also, with the first one, the
Yeah,
question in my mind was, so you took it out to 5 cycles there, but say the cell is, they say that it goes to 1,000 cycles. I doubt it, but
right.
anyway,
Yeah,
imagine that there's a large number of cycles, and we only saw it after 5. You see a lot of motion there, but we also don't see what it looked like at 45 cycles or 500 cycles, for example. Does it calm down to a slower rate of change? Or is it once again, you looked at it such a short time right at the beginning of the use of the cell that it hadn't yet electrochemically settled down into its normal pattern? Is this relevant to the user or not? We can't tell from this, but a little bit more tail on the testing might have helped there, I think.
well, I tested it for 16 cycles. I just showed, I think,
Okay.
about 5 just because it was super like compressed in the graph. It was hard to see.
How did it
Um,
look?
and it continued that trend. It was like trending
Okay.
upwards the entire time. Now, from my other testing of commercial cells, they are shipped already calmed down, as you say, right?
Yeah.
They go through that formation, they go through an aging, and then they're already in that electrochemically stable phase, right? Like a more developed SEI. For a research like battery, I would agree with you, right? You're measuring the initial state of the cell, the current state of the SEI, the interfaces, when you're
Yeah.
using a technique like this. So you need to establish kind of that stable behavior before making a judgment. But I'm judging these harder because they're already supposed to be at that phase when they're sold.
Yeah, so I can imagine a manufacturer out there that realizes that most people don't have this uh, test equipment, and
Mhm.
failures in the field is one way of measuring whether they should have done that or not. But the feedback from that is very, very rough.
That's
Um,
true, yeah. Mhm.
and if it's less expensive, they get the contract. If it's too much more expensive, then they don't get the contract, and they're basically selling some of their B stock instead of A, just to get yields up, which would seem problematic unless nothing ever happens to their customers. But we can't see that until we see feedback from the field. And so they
Right,
might just be
right.
risking their reputation in the field because most mom and pop users of coin cells picked up at the grocery store aren't going to
Yeah,
know what it was.
exactly. Yeah. Now, like for putting it in like an air tag or something, like I wouldn't see like a big safety risk here. Because it is just a rechargeable coin cell. So that's probably what they're thinking. Just a small amount of mass in the material. So it's a low risk for liability relative to something like a cell phone battery. Um,
Eric, oh, sorry, let's go ahead and Jeremy, finish your.
yeah,
Oh,
here we're looking at larger format cells where we're not really looking at safety, but we're looking more at performance. So this is an exercise that I started for cell qualification. So when you're purchasing cells, how do you tell which one is better in like a shorter period of time through this technique? So yeah, this is similar to what you were saying, Michael, about using this to detect counterfeit cells. What I did was kind of the opposite, where I bought 3 aftermarket cells that were from less reputable brands, marketed for things like vape pens or aftermarket e-bike cells. And then I got one really nice name brand cell. And I mixed them together, made them anonymous, and we can kind of go through the data and see if we can tell which one is which. So these are all commercial, purchased 18650s, the same capacity, so we don't have to do any normalization. And there is a photo of one. So we're going to use calorimetry. Here is just the raw data, so you can see the differences in the thermogram. Right, most of them were NMC. Cell 1 was a lithium manganese oxide. So we can see some differences there, right? These little rabbit ears. Cell 2, 3, and 4 were the same chemistry, but we still see some differences. So there are slight variations in the formulation or the quality of materials. Right now, when I'm interpreting this data, I usually kind of use different calculation methods to look at the thermograms as a whole, rather than trying to interpret an individual peak in most cases. So now this is a little bit of background theory, right? Encompassed in this total heat flow measurement, right? We have the reversible heat from the reversible energy storage reactions. This is structural changes in the active materials, phase changes, the energy storage reactions themselves. So everything that's supposed to happen in a reversible rechargeable system. Right. We have the contribution from the resistance, so the Joule heating effect. So dependent on current and the internal resistance of the cell. And then we have everything else, so all the side reactions. So this is what causes some of the asymmetry, so the non-reversible parasitic reactions. Now, this is also an umbrella term, so not just the interfacial reactions that cause SEI growth, but anything that's not reversible in the cell that produces heat flow will be encompassed in this as well. So we're going to show the equation, but we don't have to go that in depth. Basically, this is taken from some of Jeff Dahn's work, where we can isolate the heat flow from just the parasitic reactions, right, by using this technique called the integration subtraction method. Our software will do this automatically, and we can plot things like the parasitic energy, versus cycle number. Right, now this has a really nice correlation with how quickly a cell will degrade. Right, we're basically measuring the rates of parasitic reactions or the kinetics of them per cycle or as a function of voltage. Right, you can see this correlates really nice with like the longer term cycle life experiments. Right, only you can do it in a much shorter period of time. Now, taking this technique a step further, we do something called like a narrow cycle parasitic heat measurement. Right, most of these parasitic reactions, when we're looking at voltage stability, high voltage stability, they're going to be voltage dependent. Right, higher voltages, we have a higher reaction rate for the side reactions. So we cycle the cell, right, in this more narrow range, about 100 millivolts, and a series of discrete steps. Right, we can measure the heat flow response, right, for those narrow cycles, calculate, the non-reversible heat, so the parasitic heat from that, and we can plot that both per cycle and then as a function of voltage. Now, when I show this data, I want to point out that, I initially plotted it as a standard deviation, but it's not really true, right? Now, these discrete measurements, these dots, this is cycle 1, cycle 2, cycle 3, right? Keep in mind, this is a passivation reaction, right? So we're measuring how quickly these reactions are pacifying, right, as a function of the cycling. right? So when we first go to 4.3, it's very high kinetics, then it starts to slow down gradually as we stabilize. Eventually, it'll kind of reach a point where it's not changing that much, but it's going to settle at a baseline that's higher than the lower voltages. Right, so we get this distribution of behavior during our measurements. We can use that to look at the passivation rate and the general kinetics as a function of voltage. So I'm going to show on the next slide the data from those 4 cells. Here's my little circles. So I plotted this with a slight offset on the x-axis just because they were overlapping in certain points, just to make it easier to see. But we can look at this and start to make a judgment, right? Now the obvious one that's bad is cell 2, right? Much higher rate of parasitic processes across all voltages, right? Trending upwards as we go higher. The other 3 cells were not bad, right? Fairly comparable in performance at the lower voltages. Now they start to differentiate a bit when we get to 4.2, right? This cell 1, a little less stable. We get to cell or to 4.3, like high voltage stability, right? The one that's the most stable here is going to be cell 3, right? We can see they're destabilizing at different rates here, but the high voltage stability, kind of the general overall rate of parasitic reaction is going to be lowest in cell 3. Now, another thing to do is to measure the heat flow during storage, during open circuit. Now, this is a common test that's done in primary cells, non-rechargeable batteries. Now, I've been approached by a few companies where they're looking for a shorter way to do this. The traditional method I've kind of put on the right here, where they basically do a thermal soak and then discharge the cell about every month. It typically takes, with the number of cycles they have to do, because their data is not really as repeatable, they look at long-term trends. So they're looking at 12 to 15 months to qualify the cells for like storage stability. So when we're looking at this, like our method, we're just measuring the heat flow, right? We have this, since we're charging it to the storage voltage, then we see this thermal relaxation, right? We're doing this at elevated temperature as well. We could see that the general slope of this, right, is different than the voltage relaxation. Right, so we're kind of measuring different processes here. And we can get some kind of kinetic information on the background. When you look at our different contributions to the heat flow, right, we're not changing the net state of charge, right, over this testing time period, at least not by a lot. So there shouldn't be any contributions from like the entropic heat. So there's no structural changes, should be no energy storage reactions. We're not passing current through the cell, right? So there's be no joule heating. So the total heat is going to be equal to these parasitic processes. In reality, you'll have some contributions from like reversible shuttling reactions as well, and then things like lithium diffusion through the active materials, like into the overhang region, for example. But those are relatively minor compared to the parasitics. Now I'm going to show the data of all 4 of those overlaid. Now I'm going to zoom in on each of these portions. That's why my plot's kind of near the top. All right, so we can see, again, our thermal relaxation. Obviously here we have cell 2, the passive heat generation is much higher than the other 3, like kind of matching our previous data. And we look at the first hour, all right, we're starting to differentiate already. All right, cell 3, which was the best on the previous test, is starting out lower. Cell 2 is the highest, the other 2 are comparable. All right, after 24 hours, we can kind of see that full trend, right? Cell 3 is the lowest. The others start to relax down, right? And then the remaining 4 days, since cell 4 is so high, I'm just going to remove that and just look at the other 3. We can still differentiate them, right? The other 3 actually relax down a little below cell 3, interestingly enough. Now, since we have some crossovers and the data is pretty close together, what you can do to make this a little more clear is integrate the total heat flow as a function of time. Right, so you're plotting the total heat generated in joules, right? And we can differentiate our cells much sooner. So this is the total over the 5 days, but looking at the 24-hour mark, right, we can see that we have clear differentiation with cell 3 being the lowest heat generated, which will be the most stable through these test conditions. Right, we have cell 1 being second, so that was our LMO cell, and then followed by cell 4, and then of course 2 was the worst by several orders of magnitude. So going back to our original slide here, right, if we were to make a judgment on these, right, cell 3, right, less parasitic reactions in all voltage ranges tested, higher storage stability. The following two are relatively tied, right, cell 1 and 4. Cell 1 had better storage stability, but cell 4 had better high voltage stability. So which one is better is depending on what you're qualifying the cell for. What do you want it to do? Why are you buying it? Right, in cell 2, obviously the worst overall in every category. This one was very poor performance. Now, as a spoiler, does anyone want to guess which one was the name brand cell? Well, it should be obvious. I think in this case, our prediction kind of, or rather our data matches what we should have predicted, is that cell 3, right, the one that was best overall, was actually the name brand one. Cell 1 and 4 were surprisingly close as far as performance goes, but we edge out a little bit in those two categories, and then cell 2 was, yeah, that was worse.
What's interesting about 1 and 4 is that they're totally different chemistries, and yet they were close in terms of your measurement performance.
Yeah, that was interesting. So you can see how this could be used, I think, both for looking at like a counterfeit cell, but also just general cell qualification, or when you're testing lots from an incoming manufacturer when you're purchasing these cells, looking if they've changed anything in their process, right? Formulation changes that might affect future quality, which I know a lot of people in manufacturing, and that stuff happens all the time. You know, they don't tell their customers because they don't want them to cause issues. But this at least will tell you, if you're looking at things like storage stability and cycle life, thermal stability, if that actually affects, that change affects your performance.
Is it SEI formation a desired reaction to a certain extent? So would you classify that there is more heat generation during rest, that is necessarily a bad thing? Or after a while, if it stabilizes, is that a good thing? I'm asking out of ignorance. Thank you.
Yeah. So SEI formation is good during the formation step. What you want in an ideal SEI is something that forms quickly, and then the kinetics of that after it stabilizes to be low, right? Because you don't want excess growth in the SEI layer. That's what causes the effects from cycle aging, right? So increase in cell impedance, like a thicker SEI, kind of reduces the intercalation kinetics as well. It also consumes lithium inventory, so your capacity is reducing. So if after that formation is stabilization, which again, these are commercial cells meant to be used, it should already be done. You don't want that rate of SEI growth to be high. You want it to be as low as possible.
Thank you. Excellent explanation. Appreciate it.
I have a question.
Yes.
Excuse me. So you mentioned that you used the potential stat for all of these experiments. Did you get a chance to measure the impedance? You mentioned the impedance growth a couple of times.
I did, yeah. So
does it match?
Cell, yes. Short answer, yes. What I like to see is with this technique is the correlation between the electrochemical data and the heat flow data, right? It's like I'm doing 2 to 3 experiments just at the same time. So when I'm looking at things like that baseline shift in the cell impedance, I am looking at like the voltage hysteresis as well, just to verify that that's a thing that's happening.
Also, in terms of your experimental procedure here, this is very, 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 very small sample size. So we see just 4 cells. If
Yes.
we take a lot of, say, a right sample size, statistically selected, of each one of these manufacturers of these chemistries, it'd be interesting to see whether one question, the worst overall cell 2, was an outlier from that manufacturer, say, and that would indicate a quality control issue perhaps, or whether it was consistently outlying in its way. And we can't tell that from here. We can't tell that it was actually a fluke or not statistically.
That's correct. Yeah,
So
that's correct.
if I'm a company and I need to evaluate A, B, or C in terms of my supplier for my battery cells for my pack, it's really hard for me to go from this unless I'm really just willing to shoot from the hip and go for a low cost evaluation. But a true evaluation would be more involved. When you actually set this up for this purpose, did you actually have a greater number of cells to choose from to actually run your experiment here?
Well, just some background on like what I do. I pretty limited budget for buying samples, so doing this in my free time for work. But what I would ideally do is have like 4 of each kind. I mean, no, that's not like a big pool to choose from, but it's better than 1 each. And that would catch things like, one cell being a fluke or damaged during transport. Another experiment idea I had was to buy like, 6 to 12 cells from the same manufacturer and look at how much variation we see within the same type of cell with the same lot. Because I know there's a lot of variation in the long-term testing oftentimes. But this is, in this particular case, more of just a proof of concept study.
Oh, yeah, I was wondering if you've ever been able to see any entropic differences between charge and discharge, and maybe you have to go to higher C rates than you are typically using here, which look like maybe 0.1 C or something.
Yeah. Yeah, I do. I mean, there is sometimes when you vary the temperature of the thermostat, which we go from 4 to 150 in ours, I see kind of differences in the entropic, how it affects the entropic component of the heat and the capacity as well, between the charge and discharge branch. Like lower temperatures for some of the cells I've tested affect the discharge much higher than the charge, which is interesting to me. I'm not exactly sure why.
Difference in the chemistry or the physical behavior of the material, I guess, in some way. But
Yeah.
But yeah, okay. But you can measure that then, and yeah, see differences.
You can, yeah.
Interesting, yeah. But is that just that you get kind of an offset between the chart? Like you'll see that you've got the plots you showed, and you'd see a distinct offset between the charge and discharge halves or something.
But sometimes it's an offset, but sometimes it's like you'll see slightly different features, like the suppression of one peak. Sometimes it's like the increase of another. Sometimes it's like when you have effects on the capacity, like you do on the low temperature testing. To get a good resolution scan, you just go slower, right, to minimize the effects from resistance. But you also want to also go fast just to see what the effect is on the impedance on the whole system. So I like to do both and kind of look at it from multiple angles just to try to figure out what's going on. But yeah.
Okay, thank you.
So any other questions?
Were all the tests done at since this is an isothermal technique, so you're controlling the temperature actively within that machine where you have the battery?
So as far as the measurement itself goes, we have this, if you can see my mouse, this isothermal calorimeter. This is a big temperature control bath. It's an oil-based thermostat, and we have different calorimeters in there. So we can run for coin cells 12 at a time, for cylindrical 4 at a time, in a simultaneous test. It'll control the temperature within 100 microcelsius or less. So it's maintaining that temperature. And as you generate heat, right, it's drawing the heat out from the cell just to maintain a constant cell temperature. And as it draws it out from the cell, we're measuring it, like it's passing through our heat flux sensors. And the same is true when we're during an endothermic process. Heat's being added from the big thermal sink that is the temperature control bath. And we have these electrically wired ampules that interface with the potentiostat.
Can I just ask, would you be able to fit pouch cells, small pouch cells in there, or is it limited to cylindrical formats?
No, you can do pouch cells. So we have a specific calorimeter and ampules for those. You can do 2 by 3 centimeter pouch cells. You can also do about 6 by 9.4 centimeter is the largest, or smaller. We've been experimenting with ways to apply a stack pressure during the measurement as well, just to open up possibilities for like solid states and lithium metal cells. We've had some good success with that recently. So excited to try that. I'm about to get it in the mail to start playing around with it.
Did I hear you say you have 12 calorimeters in there? In other words, you can test 12 cells at a time?
Yep, I can. For coin cells.
Second question, the C rate, someone mentioned you're using C/10 rate. Is that right?
That's what I was using in this case, yeah. Now, when you go slower, you get a more precise measurement. Like generally speaking, not slower than C/10. But your heat generation is a little lower, right? Because everything's just moving a little slower. When you go faster, a lot of the events are kind of closer together, right? So your resolution in the thermogram is a little lower. But there's still use in measuring like the total heat generation, even at like faster charge conditions. So there's use in both. So your experimental parameters like the C rate, it really depends on what you're trying to measure.
What's your
To make an obvious point, if you are using very fast C rates, you are overweighting the internal resistance related Joule heating. Whereas if you go to lower C rate, then the entropic effects are highlighted, and so are the effects related to the side reactions during open circuit and even during operation, because the side reaction may occur at a rate and that heat may be masked by I²R heating. Just an obvious point that you have already mentioned. Thank you.
No, that's a great thing to point out. So when you're measuring parasitics, I think the kind of the sweet spot for a really accurate reading is about C/20, right? Just for the exact points you mentioned.
You're awesome. Really, under a shoestring budget, you have done so much good work. Congratulations.
Thank you. My
So
budget's not quite shoestring because I have 2 of these calorimeters, but my budget for samples is small.
So just one other question about the C rate. Yeah, what it looks like you have to pass the current. You've got the sample holder there that you pass the current through. Is there a limit on how much current you can put in? Your connection size or something?
For the electrical wiring, I mean, there's recommendations. That's something that we can change, but what you're limited by is the dynamic range of the calorimeters themselves. So we have a couple different potentiostat models that can apply. I think some of them apply up to 3 amps. I think we're going to partner with another one that goes up to 6. But typically we're looking in the milliamp range for things like coin cells. Now, when you go to larger format cells, like a 21700, for example, and you try to do fast charge testing, then you start to get into that range where you're just saturating the detector, right? Because you can't have high sensitivity and high dynamic range. Like it's one or the other. So this really shines with the low sensitivity measurements, but we can go up to like, you could do fast charge in coin cells and small format cells, larger format cells, then you're kind of pushing it with the fast charge requirements.
Okay. Thank you.
Now, having said that, I have done some fast charge stuff on like the coin cell level and small pouch cells. That works fine. Some of the larger calorimeters, like I said, for the 21700s, that's where I was running into issues. I could go up to like about 2 amps, which was like, ended up being about C/2, I think, for the cell I was testing. So, and then it started to saturate the detector a little bit above that.
Right.
Well, let's take a look at that because if you're doing power cells and that's actually what your market is, and you're actually looking at large formats because that's what your clients want, then this is only useful as a lab device. But if I actually want to use it in concert with qualification for my military customer that has high requirements of due diligence on these, but we're basically looking at a power cell that has way over 10C discharge. Can you not create a device that would then be tuned for high discharge?
Yeah, that's a two-part question. So I'm going to answer your second one first. Yes, we could. That is just it's just an engineering thing. It's something we're looking into for like a next gen product, just for more flexibility. The first part is, just because you have a power cell doesn't mean you can't use some of the techniques I showed to evaluate it. Because it's really a different type of thing that you're looking at, right? A power cell, if you're looking, I guess I'll give an example where a company approached me. They were looking for a cell qualification for their power cells, but it was going to be used as like a backup battery, like in a server room. So very high discharge rate, about like, 2 minutes. And it would be fully discharged, but it was also going to be stored in a warm room for a long period of time. So we were doing a combination of, the voltage dependent parasitic reactions to look at the propensity of those long-term degradation processes to happen as a function of voltage. And that helped them figure out what voltage to store at, right, for maximum lifetime. And we also looked at the heat flow during open circuit, as I showed. Right, this shows you in a more practical way, like at elevated temperatures, what is the thermal stability and rate of background processes during storage. Now, they coupled that with just a very fast charge-discharge cycle life test. At the rates they were going, it only took them a week. We're not talking months for these power cells until they saw some sort of failure. So they also ranked the cells using that technique. I saw them as very complementary, for an application like that. There is use in that direct application types of testing, but just because it's a power cell doesn't mean you have to charge really fast. Right? There's other ways to evaluate the chemistry.
Andrew, you need to get some oil damping on your keyboard there.
Oh, thank you.
Does that answer your question?
Yeah, so the charge cycle and the discharge cycle are typically quite different in those applications, so you're right.
Yeah.
If you can basically qualify or characterize your cell at lower cycle rates, lower C rates, then that's fine, but you kind of have to prove that too. So you need a device that can show that that is the case. So that was good. Thank you.
Yeah, that is something we're looking for. We have a few candidates right now, but looking for people with these large historical data sets where they're still making the same type of cell, where they have a lot of the, the years long with a bunch of, different cells they've tested, the cycle life, the storage stability, and then we can do our short-term measurements and kind of compare the long and short to see how they match up. But a lot of people are really secretive with that type of data.